Okay, so we're continuing our exploration of the motion of rigid bodies in 3 dimensions, and we're going to pick up by taking a look at Eulerian angles. Um, Usually people wind up being lazy and saying Euler angles, but it's actually correct to say Eulerian angles. Um, so we've been seeing so far that it's really convenient to do moment of inertia calculations in the body frame, the frame of the object that's actually doing the rotating. And so we need some sort of prescription for how to transform to our fixed or lab frame. Um, and of course, Euler came up with a way to do that. Now, just as a bit of a heads up, um, I am going to deviate from your book's notation a bit. The prescription that we seek to get is that x, which in the notation I'm following is in the body frame, will be equal to some transformation matrix lambda that we dot into our coordinates in the fixed frame. Now, the prime notation is swapped with respect to your text, although the angles phi, theta, and psi will follow the same convention in the same order. So I did that mostly because I wanted to steal this picture here, which I then blew up a little too big, so I'll try to tell you what you're seeing here. So we start out, we've got our x1 prime and our x2 prime axes here. And the first prescription is that we rotate our coordinate system through some angle phi about the x3 prime axis. So the new x3 double prime will be the old x3 prime, but then this is my new x1 prime and my new x2 prime. The next step is to rotate through some angle theta about the 1 axis, the new 1 axis, not the old one, but the new one, so x1 double prime. So that will make that the new triple prime coordinate. And so this will move the x3 prime slash double prime over to x3 triple prime here, and that will be the final location for our new x3 axis. So what you do is you first rotate here through phi so that you can get the right angle to turn this into its final position, which we now do through some angle theta. And that will have the effect of also hiking up our x2 double prime over to x2 triple prime, like so. And then the final step is to finally get our to our x1, x2, x3. So our x3 triple prime, since this isn't moving anymore, we're going to rotate about this new 3 axis. That just becomes our x3. And by this, then also here, my x1 triple prime, which was sitting here, gets rotated to its final home right there, x1, and x2 triple prime gets rotated through its home, x2, both about the x3 axis through some angle psi. So kind of the way I remember it anyway is just think about the area code for Metro Detroit, 313. So first you rotate about the 3 axis, then the 1, and then the 3. And I also can kind of remember the angles a bit. This is phi, which rhymes with 3. Theta doesn't rhyme with 3, so it must go with 1. And although we always say psi in English, the correct Greek name is psi, which rhymes with 3. This one we tend to use more, so this is the one I kind of go to first. So that's how I remember the order phi, theta, psi, 3, 1, 3, being the axes about which we rotate. Okay, so that's the prescription that we're going to use. So thinking back to the first chapter when we were looking at coordinate transformations, my first rotation to get to the double primes is going to be to rotate through some angle phi, so I need a transformation matrix to do that. My old x prime. Okay, so we remember what that is from, we remember what lambda phi is from when we looked back all the way back in chapter 1. That's going to be cosine phi sine phi 0 minus sine phi cosine phi 0, 0, 0, 1. Okay, so that's the first rotation. The second rotation will be about the one-axis, and it'll be by some angle theta. So this gives me x triple prime is equal to some lambda theta dot into the x double prime that I had. And so since we're rotating about the one axis, my lambda theta has to be 1, 0, 0, 0, 0. Then we have cos theta, sine theta, minus sine theta, cos theta. All right. I'll make it look a little prettier. Then finally, our third rotation is going to, that gets us to our final destination. X is going to be equal to lambda psi dotted into x triple prime. So again, this is back about the 3-axis. The only difference, in fact, I am going to be lazy and just copy this. So my lambda psi tensor would have to be, now let's move it into place, almost that. The only difference is we replace the phis with psi. There we go. So our general, oops, there we go. So our general rotation, our general transformation then is that x is going to equal lambda psi dotted into, well, x triple prime would be lambda theta dotted into, well, that would be x double prime, which is lambda phi dotted into, finally, my x prime. So we have found a prescription for writing our transformation matrix lambda. There it is. And so we can go ahead and write it out. So my, whoops, my, doggone it, my lambda will be, so what I had before, cos psi, sine psi, 0, minus 0, 0, 0, 1. The theta matrix is 1, 0, 0, 0, 0, cos theta, sine theta, minus sine theta, cos theta. Move that 0 over and make it look a little prettier. And then finally, cos phi, sine phi 0, minus sine phi, cos phi 0, 0, 0, 1. All right. And because I'm going to need part of the result later, I will actually dump on you what the entire product is when you do it. you should convince yourself that this is true. Okay, I basically just dumped it into Mathematica and went go. So we'll have cosine psi, cosine phi, minus, cos theta, sine phi, sine psi. And I'm going to kind of section this off into a tic-tac-toe board here. Minus sine psi, cos phi, minus cos theta, sine phi, cos psi, sine theta, sine phi. Here we get cos psi, sine phi, plus cos theta, cos phi, sine psi, minus sine psi, sine phi, plus cos theta, cos phi, cos psi, and then we have minus sine theta, cos phi here. Oops. And then the last column of the tic-tac-toe board is sine psi, sine theta, cos psi, sine theta, and then just plain cos theta. So hey, at least one of the entries looks not too bad, and these aren't that awful. Well, these are god-awful because all three angles wind up showing up in them. Okay, so I agree. This is a total mess. I mostly went ahead and presented this because we're going to need to get this part of it later. All right. So now let's work on developing the similarity transformation. For our moment of inertia tensor. Fancy way of saying boosting it into a different coordinate system. So let's go and take a look at how we can transform our I to different coordinates. And I'm going to go back to using tensor notation or index notation here because it's going to be a lot easier. So the moment of inertia, so the angular momentum is going to be the dot product of the moment of inertia tensor with the angular velocity. And that's how, whenever you look at that, that's how you should see it. If you're contracting two indices, there's a dot product involved. So in our rotated system, we would be writing, say, some Li prime would be equal to sum over j, and it'll have an I prime of ij omega j prime, like so. We're going to call that guy star. Now, we can transform my Li prime to, in my rotated frame, into my non-rotated system, into my body frame here. Li will equal sum over j lambda ji Lj prime, like so. And similarly, we can do that with the omega. Omega I would be sum over j lambda ji omega prime j. Now, we need to get this to be a nice convenient matrix multiplication. It'll be convenient to swap the order of the indices here. So this bit will become a sum over j, and this would be lambda, lambda ij, but it had to be lambda transpose Lj prime. And by the same token for my omega I, that would be sum over j. And I'll have a lambda ij, again that would be transpose omega j prime. All right. Super. So with all of that, my star up here becomes, that'll be sum over m, lambda mk lm prime, boosting this over to the body frame, and similarly sum over L, IKL. So we're boosting our I omega over. So this first bit, this first sum over L is just for the I, and then we need to boost our omega over. So we'll pick up a sum over J, lambda JL, omega J prime. All right. Now what we're going to do is we're going to multiply through by lambda ik, and then we're going to sum over k on both sides. That's totally allowed. And I can commute the sums, which is exactly what I'm going to do. So I get sum over m, sum over k, lambda ik, lambda mk, lm prime be equal to sum over j times sum over both k and l of lambda ik, lambda j, jl, ikl, omega j prime. All right, now if we look at this piece here in the parentheses, I can do the same trick as before. I can swap the order of these indices as long as I'd make it the transposed matrix. So it'll become sum over k, lambda ik, lambda km transpose. But since the matrix is orthogonal, there'll be sum over k, lambda ik, lambda km inverse. And so that's just the Kronecker delta, or a fancy way of writing the identity matrix. So since all this is just summing over the identity matrix, that just converts this m index into an I. So the left-hand side becomes Li prime. Okay, the right-hand side, I can't do much with at this exact moment, but don't worry, we'll keep digging at it. Sum KL, lambda ik, lambda jl, ikl, omega j prime. And this bit here we recognize is my transformed moment of inertia, ij prime. Okay, so let's look at that piece. All right, so that piece, ij prime, set as sum over kl of lambda ik, lambda jl, ikl. All right, I can commute these two for free, so I will. Sum over k and l, lambda ik, ikl. And then here with this lambda jl, I'm going to write as lambda lj transpose. But since it's orthogonal, oops. And since it's orthogonal, I can just replace that transpose with an inverse. Now I look at this and I realize I've got dot products. So I can write this as my I prime is equal to lambda dotted into I dotted into I inverse. So in order to transform from one coordinate system, transform a rank 2 tensor, a matrix, from one coordinate system to the other, we need to actually do two matrix multiplies, one on either side. All right, So with that little aside, we can go back to our Eulerian angles. So, in general, rotations do not commute. If you don't believe it, try taking your book, rotating it first about the long axis by 90 degrees and then the short axis by 90 degrees, and then try it the other way and see if you get the book pointing the same way. You won't. And it's a good thing that rotations don't commute, otherwise you couldn't parallel park. But it turns out infinitesimal rotations do commute. So that means that I can write omega dt as being equal to a d phi plus a d theta plus a d psi. And so then that becomes omega, I can interpret as d phi dt, or phi dot, plus theta dot plus psi dot, like so. Okay, so that's super helpful. So now we just need to go back and figure out our components of our phi dot, theta dot, and phi dot. So let's look first at the phi dot. So if we refer back to our figure here, this badly mangled thing here, oh, it won't let me draw on it for some reason. This badly mangled thing right here is phi dot. Oh, it's doing some funky kind of layer action on me. All right, we're not going to mess with it. All right, so this is phi dot, trust me. And this is theta dot while we're at it, and then this is psi dot right here while we're at it. So this is my phi dot, and the main thing is that I want you to see is that points along my 3-axis. So I can write phi dot as being lambda dotted into phi prime. So phi dot prime is equal, and remember phi dot prime is equal to phi dot times E3 hat prime. All right. So if I take this guy here and I dot this monstrosity in here, the only things that's going to give any contribution is this last column here, thank God. So we can write then that my phi dot is equal to phi dot sine theta sine phi E1 plus phi dot sine theta cos phi E2 plus phi dot cos theta E3. Phew. Theta dot is not quite so bad. To get my theta dot, all I have to do is look at these two transformations here. So my theta dot becomes lambda psi dotted into lambda theta dot into theta dot double prime. All right. So you go ahead and do the matrix multiplies, and you will get theta dot cos psi E1 hat minus theta dot sine psi E2 hat. Whew. And then finally, the easiest one is psi dot. That just equals psi dot E3. So we can collect our E1, E2, and E3 components to get the components of omega. So omega 1 is psi dot sine theta sine psi plus theta dot cosine psi. My 2 component of omega is phi dot sine theta cosine psi minus theta dot sine psi. And finally, omega 3 is phi dot cos theta plus psi dot. All right. Well, that seems pretty hairy. So I think now is a good time as any to do an example. So let's say here's my x1 prime, x2 prime, x3 prime, and how I want to end up is we'll keep, that'll become my x1 here, and then, oops, I'm sorry, that won't become my x1, my bad. I'm going to move my x1 so that'll be in, so they'll be in the x2 prime, x3 prime plane. Nice 45-degree angle. So that's going to, and then I'll have my x3 be over here there, and then I need my x2 to be mutually perpendicular to both of those guys. There. All right. So we go ahead and think about the rotations we need. The first thing we want to do is we're going to want to move our x1 prime to an x1 double prime that will correctly locate my x3 prime over to x3. All right, what's going to work really good for that is just no rotation whatsoever. So my lambda phi, and just like I said, we're already, this is in the plane we want. So I don't need to twist this to get into the plane I want, it's already there. So my lambda phi is just going to be no rotation, so that's the identity. All right. Now the next step is I'm going to want to rotate about my x1 prime, which turned out to also be my x1 double prime. So that's the 3, 1. All right, so now I need to rotate that over to get my x3 correctly located. So we'll do a 45-degree rotation for that. So my lambda theta will be 1, 0, 0, 0, 0, and then my sines and cosines are all going to be 1 over root 2. Super. Then finally, now that I've got my x3 prime where I want it, so my x3 turns out to be also my x3 double prime there. Sorry, my x3 triple prime. So now we go ahead and rotate about x3 to bring this over to there. All right, so that will be lambda psi equals And I'm going to need to do a 90-degree rotation on that. So my sines and cosines will be 0, 1, 0, minus 1, 0, 0, 0, 0, 1. So my general rotation matrix, or transformation matrix, will be lambda psi dotted with lambda theta dotted with lambda phi. So that will be equal to 0, 1, 0, minus 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 1 over root 2, 1 over root 2, 0, minus 1 over root 2, 1 over root 2, and the identity. Well, this dotted into the identity is just going to be itself. So really I just need to do the matrix multiply of those two. And when you do, you get that your transformation matrix is 0, 1 over root 2, 1 over root 2, minus 1, 0, 0, 0, minus 1 over root 2, 1 over root 2. All right, so recapping what we've done here, basically if I need to transform from one coordinate system, transform my coordinate systems from one to another, easiest way, or at least an easy way that Euler came up with, and he proved was all you need to do was at most 3 rotations. And remember, you go about 3, 1, 3. So you first rotate the about the 3 axis to put the 1 axis perpendicular to the plane that will be defined by the new 3 and the old 3. You then rotate about the 1 to put the old 3 over to the new 3, and then you rotate about the new 3 to put the 1 and 2 axes where you need them. So maximum 3 rotations, and Euler proved that. And also, if you decide that you need to transform a tensor, that is going to involve multiplying by a lambda in the front and a lambda inverse in the back. Okay, that was a big mouthful. In the next video, we'll go ahead and use some of this machinery to let us look at things like the motion of a top.